At this stage, the joint is made. Now we want to detect if there are defects in the joint without destroying the joint. That's non-destructive tests. That will be the theme of the Module 7 Quality Control. We have manufactured the joint. Now it's time to control the quality of the joint. That's what we are going to discuss in this module. But I also take the opportunity to discuss quality control in terms of the adhesive, the adherent, and the manufacturing process. In terms of the adhesive, actually, we have already discussed this when we have studied how we can characterize the adhesive mechanically, the strength test, the fracture mechanics test. But there is another test that is very important for quality control, which is the one that enables to determine the glass transition temperature of the adhesive. It's very important, this property, because a structural adhesive is only structural if it's used below Tg. So it's important to measure exactly Tg. One of the most common methods used is the dynamic mechanical analysis. Very, very simple test. We have a beam, a specimen that we oscillate with a sinusoidal stress wave, and we measure the response in terms of strain, and we measure the phase difference between the two. When we are at Tg, we have maximum damping and the phase difference is maximum. So if we record this during the test, at Tg we have a maximum in the damping, and that's how, in general, it is measured, the Tg.
I'm going to talk about this machine that we have that is called a glass transition temperature measurement device. This machine is used to determine the glass transition temperature of polymers, such as the adhesives that you see here. So how does this machine work? We have this specimen, which is a beam, and this beam has adhesive inside this constrained layer that you can see here. So there is a metal sheet. The adhesive is located here between the layer and the beam, and it's fixed in position by a screw. Then this beam has two magnets on each side. These magnets are going to be driven by these coils that you see here, and they will impose a vibrational movement to the specimen. So the specimen will flex down and up, down and up. And this will load and unload the adhesive layer. To determine the glass transition temperature, what we need to do is use this oven to increase the temperature gradually until we reach a point where the specimen damping is maximum. This means that the adhesive has reached the glass transition temperature, and during this transition it becomes very capable of absorbing these vibrational movements, and this will be reflected into a peak of damping. So we will insert the specimen within our testing machine, and we will start the software that will put the specimen in resonance, increase the temperature of the oven, and then detect the glass transition temperature.
About the adherent, we didn't discuss the mechanical characterization of the substrate because we assume that this is something that is known, but we have discussed a property that is very important, which is the surface energy. So we should also control this. There are many ways to do it. The most common way is to measure the contact angle of known liquids at the surface of the substrate. If we know that, then we can deduce the surface energy of the solid using Thomas-Young equation. It's not exactly the same as the original equation, because you have here polar and dispersive components. And if we want to determine the polar and dispersive component of the surface energy of the substrate, then we have two unknowns. That's why we need two liquids to determine the corresponding theta angle to solve this equation of two unknowns. In general, we use more than two liquids. We'll use three liquids. And then we have an additional point that gives us better results and gives us a better estimate of the surface energy of the solid. About the manufacturing process, there are many points to check. It's all more or less obvious. For example, the shelf life, be careful. Don't go over the shelf life, which is in general 6 months. Be careful with the conditions of the laboratory, the temperature, the humidity. Be careful with the tools that you use, they should be clean, etc. Things that are more or less obvious. This is a very important slide which contains the types of defects that a joint might have. And these are the defects we are looking for. Sometimes the joint is not perfect and we want to detect these defects. So which kind of defects we can have? We can have a crack because we had too much residual stress during the manufacture, or in service a crack is formed. We can have porosity because of air entrapment, for example, between the film and the substrate, or because we didn't apply enough pressure in case of the adhesives that cure by condensation. This bond close to the surface or in the middle of the adhesive because we didn't put enough adhesive. Poor cure because we didn't mix properly the resin and the hardener. And all these, fortunately, they can be detected, more or less. But there is one that cannot be detected, which is a weak adhesion. There is contact between the adhesive and the substrate, but not as strong as it should be. This is, at the moment, nearly impossible to detect. How do we detect the defects? Well, we could destroy the structure. We take a wing and we do a proof test to see if, in fact, there are or not defects in the structure. But obviously, this is not sustainable and it's way too expensive. After the test, by the way, it's always important to check the fracture surface. It gives us a lot of information about the joint design, if it was well done, about the surface treatment, etc. So it's good to analyze this very, very carefully. We are looking for cohesive failure. Sometimes the failure is close to the interface and we are not sure if it's really adhesive failure. It's good to check the surface in a scanning electron microscope to make sure that in fact it is adhesive or not. In this case, it's a typical case where we have a hybrid or a mixed failure, adhesive, cohesive. There are still marks of adhesive at the surface of the substrate. But in fact, what we want is a method that can detect if my structure has defects without destroying the structure. We are talking about non-destructive tests. And the first method that we can use, of course, is our eyes. Our eyes can already detect a lot of defective joints. And you have here examples. I can also give you some examples with the joints I have in hand. So let's start with the perfect joint. You see, we can see that there is no adhesive missing all the way. The fillet, the spew fillet, the excess of adhesive that is formed at the edges is nice and regular. This one seems perfect joint. Now let's look at other joints. For example, this one, you can see that there is a lack of adhesive clearly. This side also is clear and it's not perfectly aligned and it's not perfectly parallel, the two substrates. So clearly we are in trouble here. Another one, the alignment here is clearly wrong, all right? And the spew fillet, the shape is not nice, it's strange, it's not nice like in the one that was formed a perfect fillet. So again, we are in trouble. And another one with a strange fillet that may indicate inconsistency in the viscosity of the adhesive. So examples that you have here where your eyes can detect a defective joint. But maybe the most important method nowadays is the ultrasonic method. So very, very simple. We send with a probe ultrasonic waves to the structure, and when the structure or when the wave encounters a defect, then there is a reflection, and by doing a scan over your bonded area, you can detect easily a defect. But there are other methods. You have thermal methods also that work quite well. Imagine you have a defect here and you hit from this side and you have a thermal camera on the other side. This defective joint will show as a lower temperature because the heat transfer will be more difficult in that area. If you heat on the same side, then the defective area will show hotter because the heat cannot transfer so easily to the other part of the joint. You also have vibration tests. You have lump waves and you have electromechanical impedance spectroscopy. They are very similar tests. So you put the specimen in vibration at very, very, very high frequencies. And when there is a defect, the response in terms of frequency will be different, and you can detect like this the presence of defects in your structure. EMIS or electromechanical impedance spectroscopy is very similar, the principle, but the range of frequency covered is larger.
In electromechanical impedance spectroscopy, or EMIS, we make use of an impedance analyzer here and of a piezoelectric element here that is bonded to a specimen or structure under evaluation. In this method, we excite the piezoelectric element with a electrical signal of various frequencies, and for each frequency, said signal will generate a mechanical vibration on the structure. Concurrently, the mechanical vibration will also influence the electrical signal passing through the piezoelectric element, and by measuring the electrical impedance of the sensor, we are indirectly measuring the mechanical integrity of the structure.
Finally, two words about techniques that can detect in some way weak adhesion. Acoustic emission, but you need to load your specimen. When you load the specimen, the trace waves will emit some sounds, and you can relate this to weak adhesion, but you really need to load, and sometimes close to the failure load, so it's a semi-non-destructive test. And another one very, very promising is the laser test. So you use laser pulses that you send to your joint, and when you encounter weak adhesion, the response in terms of ultrasonic waves that are generated will be different. The problem is that with the laser excitation, you might destroy the joint if you have a weak adhesion. So in fact, this can be a destructive test if it's not well controlled. But the first results that we have are very, very promising. So that's it for the quality control. You have a series of tests that can be used to detect the defects, typical defects. The king is the ultrasonic method, and the holy grail still is weak adhesion. It's very, very difficult to detect weak adhesion.